You have an application, a database, a cache, and a search index. You need all three of these data stores to stay perfectly synchronized. So you write a piece of code that tries to update all three at the exact same time. But networks are unpredictable. Your database saves the change perfectly, but your cache drops the connection and times out. Now your database says one thing and your cache says another. Your systems are out of sync and your application might not even realize it. Change Data Capture, or CDC, throws away this multiple write approach. By using a tool like Debezium, your application only ever writes to the database. That is the only step. Instead of relying on application code to orchestrate multiple updates, CDC shifts the work to the database itself. It listens to a hidden, unbreakable diary of events that your database is already keeping. Every time you save something in a database like Postgres, the data doesn't go straight to the main storage drive. First, it gets recorded on an append-only tape called the write-ahead log. Every single insert, update, or delete drops onto this tape and flows downstream. But this tape is difficult to read. It contains low-level physical storage instructions, like memory updates, that make no sense to an outside application. To make it useful, the database uses a built-in translator called logical decoding. A plugin, like PG Output, accesses this translator. It grabs raw storage instructions off the tape and rewrites them into a clean, readable format, showing exactly how a record changed. This translation step is the bridge. It takes a highly technical file meant only for recovery, and it turns it into a real-time, steady stream of business events that other systems can easily understand. To actually catch this stream of events, we place a physical net inside the database called a replication slot. This acts as a strict contract. When the database tries to clean up old sections of the tape to save space, the replication slot locks them in place, guaranteeing nothing is deleted until it has been safely read. Now, Debezium connects to the database. It disguises itself as a standard backup replica, attaching directly to that net. It reads the translated events in the exact order they happened and siphons them off to a message broker like Kafka. As Debezium passes these events along, it waits for Kafka to confirm they arrived safely. Only after receiving that confirmation does Debezium tell the database to move the net forward, allowing the old tape to finally be deleted. Because Debezium acts as a native backup client, it never has to ask the database for updates with expensive queries. It just sits quietly downstream, catching the changes that the database kernel pushes to it automatically. Before Debezium can stream real-time updates, it needs to know what is already in the table. So it temporarily pauses, bulk copies all the existing rows to establish a complete baseline, and then seamlessly switches back to catching individual updates off the moving tape. Looking at this JSON payload, you can see that every update Debezium sends out is wrapped in a consistent package called an event envelope. It shows exactly what the row looked like before the change, what it looks like after, and the specific operation that happened, like the letter U for an update. Because this package is so predictable, your external search index or cache now has the context it needs to update itself directly. It doesn't have to go back and ask the primary database for help. The event contains the whole story. This system is elegant, but it hides a massive operational risk. If the Debezium connector crashes or goes offline, that internal net, the replication slot, stays right where it is. Without Debezium to read messages and move the net forward, the system clogs up entirely. Remember, the database is contracted to never delete unread tape. As new writes come in, the tape backs up, consuming more and more hard drive space. Eventually, the server hits 100% disk capacity, and your entire database freezes, halting all operations. Looking at this monitoring dashboard, you can see how teams prevent this. You must configure strict safeguards, like setting a hard cap on how much tape the database is allowed to keep, and setting up an alert that fires immediately if the replication slot goes inactive. An unmonitored CDC pipeline is a ticking time bomb. Deploy it without these safety limits, and a simple connector crash on a Friday night can bring down your entire infrastructure by Sunday morning. There's another reality to this architecture. Debezium guarantees your message will arrive, but it doesn't guarantee it will only arrive once. If Debezium successfully sends a change to Kafka, but crashes before it can save its own bookmark, it will wake up, read from its last known position, and send that identical change again. This means the services receiving these events, like your caches, must be designed to safely handle seeing the same message twice. Think of it like a light switch. If you flip it on 5 times, the result is the same as flipping it once. Your systems need that same logic to avoid getting confused by duplicates. In this code, you can see the service extracting a sequence ID, which is essentially a position marker on the log tape, along with the row's primary key. By checking these unique markers against a list of things it has already processed, the consumer can safely catch and discard any duplicate events. When you implement this at a larger scale, you face a choice. Reading events directly from main database tables means tweaking a column name risks breaking downstream consumers. Alternatively, write changes into a dedicated outbox table, creating a clean, permanent contract specifically for Debezium to read. Change data capture is a potent tool for untangling complex applications. By understanding how the database physically stores logs, preparing for disk failure modes, and writing resilient consumers, you can keep dozens of systems synced without ever writing a dual write again.